Hello, this is lecture 6, uh, frequency response and filter design. This lecture has two big components. One is Bode plots and the other one is analog filters. In this video, I'm going to talk about basics of Bode plots. There will be a couple of other videos where I will do some examples. Bode plots. So what is a Bode plot? I'm at this here. So Bode plot shows the magnitude and phase of a complex number. That's a simple answer for the question, what's a Bode plot? So if you look at this example, I have two examples here. One is a function, a complex number which is a plus jb, and I have another complex number which is h omega is equal to a plus j omega. Now, if you look at the left side, as I said, the Bode plot is a magnitude and phase of a complex number. So the magnitude of the complex number h on the left side is just a squared plus b squared, square root of a squared plus b squared. It doesn't change with omega because there's no omega, which will make clear when you look at the right side. Again, the phase is a constant. It doesn't change with time. So this is on the left side, this is constant. We are not interested in this type of complex number because we will see as we move along, we will be interested in system transfer functions with frequency, where things change with frequency. That is what we are interested in. On the right side, we see another complex number that's a function of omega. H omega is a plus j omega. Here, if you look at the magnitude is a squared plus omega squared, square root of a squared plus omega squared. So as omega increases, a squared plus omega squared is also going to increase. So this is something that's going to change with omega. Same with frequency. Tan inverse omega over a, that's also going to change with frequency. So how to plot? So once again, to summarize, Bode plot is the magnitude and phase of a complex number. So the magnitude and phase we will draw separately. In this video, I will conclude by talking about some other features of a Bode plot. For example, look at this function here, which I'm going to highlight. This function. This is a typical transfer function. We spent the last lecture, this is a Laplace domain. We, took this type of transfer function and we found the time response. So this Hs is actually the Laplace transform of the impulse response. To find time response, we just find the inverse Laplace transform for a given input. The Bode plot takes us for a different type of analysis of a system. First of all, first, we want to learn first how to draw Bode plots of linear system that are usually in this form. So usually we can always a Bode plot, we will take a transfer function and we will draw the magnitude and phase. That is a goal here. A couple of videos I'm going to explain several examples of how to do a Bode plot. Now, some basics we will need moving forward is this. We will do the Bode plot in log. So if we go back here, instead of this, I will actually draw 20 log magnitude of Hs. That is what we will be drawing for magnitude. There's a reason for that. That is what is being explained here. So instead of Hx, if I take 20 log Hs, you will see 20 log Hs is 20 log one component plus 20 log two component, second component, like that. So now as it is shown in the box here, that is 20 log, so log x1 plus x2 plus not plus x1 times x2 times xm divided by y1 y2 yn can be written as summations. So this log on this side can be written as log x1 plus log x2 plus log xm minus whenever whatever that is in numerator adds and whatever that is in the denominator is subtracts. So we will use this property a lot in making the Bode plots in the future, and that is what is explained here. I'm going to, not going to go into the detail. You can just look at this, but we will do several examples later. Now, to sum up here, the log 20 log HL, H omega is the magnitude plot, and then angle is, we will find the angle using different ways, like tan inverse B over A for the examples here, B over tan inverse B over A, but we will do more example too. That's what to summarize Bode plot, that is the magnitude and phase of a complex number. So that is a magnitude and that is a phase. So magnitude, instead of plotting the magnitude, we will take it 20 log base 10 magnitude. The reason is that allows us to do the Bode plot fairly easily, especially when h omega is a pretty complex number. So that's what we will spend some time on. And then we will also spend time on how to find the phase. So this equation here tells that the phase can also be decoupled into summations. What used to be complex multiplications of complex numbers can be brought down to summations if you use the log form. Alright, so that's the end of the part 1 of the video. In the next video I will introduce log scale and then do some examples.